Well, good afternoon and welcome to the University of Washington Botanic Gardens and NHS Hall, where we're going to make this afternoon's presentations. My name's Tom Hinckley and I'm the interim director for the School of Forest Resources. I don't know how many of you are aware, but the United Nations declared 2011 as the International Year of Forests. And very early in the year, the school, namely Mac Hoagland, who's an affiliate member, decided we ought to take advantage of this theme and work out a series of events that we would hold throughout the year. So this Denman lecture is just one part of a theme, and I'll talk more about the context for the theme. But we're today going to have sort of vignettes into a whole set of projects that we have that involve some aspect of international presence or a history of international connections. And so let's begin. There's a long-term tradition within the former College of Forest Resources and now School of Forest Resources in hosting international students, but around 1960, at least for the date that I could find, was sort of our beginning, sort of big entrance into an international arena, when the University of Washington, through the College of Forestry at the time, hosted the 5th World Forestry Congress on campus. And there's an international grove of trees over by Condon Hall along the boulevard there that they were planted as a result of that particular Congress. Members of then the college were instrumental in establishing the Organization for Tropical Studies, which now continues. It's hosted at Duke University, but it was originally hosted by the University of Washington. Dean Bethel and Bill Hathaway were instrumental in that. In 1984, then Dean Thorold worked with the state legislature to initiate the Center for International Trade in Forest Products. Thanks to Ivan Easton, which you will hear about later, we host the Peace Corps Masters International Program. And more recently, we've hosted through the National Science Foundation a series of integrated graduate education and research training endeavors, urban ecology with host countries of Germany and Norway, and the multinational collaborations on challenges to the environment, which hosted many nations around the world. So we'll learn more about those today. Back to the International Year of Forest, sort of the first event was Sustaining Our Northwest World lecture series by Nalini Nadkarni, and then just Friday of last week, 3 distinguished alums came and provided really insights to both their careers and their engagement in the international setting. And the Denman series today is a continuation of this theme, and then in the fall there will be an exchange with the University of British Columbia, and that will probably be the last sponsored event. We have a lot of examples. Nalini Nadkarni's head poking out through a tropical canopy is one, but we have many more recent endeavors where either individual faculty and staff or groups of students are going internationally and spending anywhere from a week to a year and engaging in research, teaching, or other sort of engagement in an international setting. And we want to talk about those particular examples today. We're very thankful to Bob Edmonds, faculty, and Ellen Matheny, staff, for organizing this particular session. And as Bob has already outlined, there's going to be 3 parts to the sessions, a series of talks, then followed by transition, and then at the very end, we'll come back for questions. Once again, welcome, and thank you for attending this afternoon's meeting. Bob?
This session is on forest and urban ecology and management, carbon cycling, and wildlife. And our first speaker is Rob Harrison, who is professor of forest soils in the School of Forest Resources. He has a BS from North Carolina State University, an MS from the University of New Hampshire, and a PhD from Auburn University. In his research interests are forest nutrition, mineral cycling, long-term forest productivity, organic waste utilization, and carbon sequestration. And he's worked extensively in Brazil, and the title of his talk is Brazilian Forestry, Intensive Management and Restoration Ecology Work Side by Side in Mata Atlantica. Rob.
Thanks, Bob, and it's really a pleasure to get a chance to talk about my favorite country other than the U.S. and my favorite subject, which is forestry. And in the interest of disclosure, I was a Peace Corps. I'm an RPCV from Tanzania, and I celebrated Peace Corps' 25th anniversary while I was a volunteer. And I want to talk a bit about intensive management relative to restoration ecology. And you usually don't think about these two things going together, but I hope I can make it make sense. In terms of Brazil, Brazil is a large country, largest country in South America, about half the area, half the population. If we take Alaska away, it's about the same size as the United States. About 200 million people in Brazil and about 300 million in the US. Brazil is the main country that has most of the Amazon. And it's largely forested. There are some dry areas. There's a lot of agriculture. And it has a pretty substantial economy going. It's mostly tropical, as you can see. If you think about what Brazil is, people think about soccer, or football, which Brazil always fields a really good team. They think about beaches. Copacabana in Rio is probably the most famous beach in the world. They think about party animals, Brazilians are, and they think about biodiversity, primarily associated with the Amazon, which is not the most biodiverse forest in Brazil. In terms of products, we have a variety of things. Cacao or cocoa that makes chocolate originally came from Brazil. Sugar is extensively, it's one of Brazil's main exports, essentially banned from importation into the US. Coffee, Brazil exports most of the world's coffee. We get a lot from Brazil. Alcohol, which is sort of tied to the sugar cane. We pretty much ban the importation of alcohol into the United States through restrictive taxes. So some of these things don't really make it into the United States, but they make it into the world market. By law, 50% of American orange juice can now be a blend of Brazilian oranges. That only happened after the big freeze of oranges in Florida. So if you turn over your can, you're likely to find a lot of Brazilian oranges. Brazil was the original country to develop rubber, and they still produce a lot of it, although it's produced all over the world. Steel, a lot of steel comes from Brazil now. And that's associated strongly with the forest industry because of the way that they produce the coal, the carbon that's used to reduce the iron ore. Cellulose wood pulp is a big export product, increasing at a very rapid rate from Brazil. And then you probably don't think of Brazil as exporting airplanes. This is probably the biggest Brazilian export to the United States is airplanes. Embraer, this is the regional jet 195, seats about 100 passengers. And until Brazil starts competing with Boeing 737, I don't think you'll probably know much about Brazilian airplanes. You've flown in these and you didn't know it, because they will not tell you, and you can't find out unless you know enough about the airplanes or ask the pilot or something. I don't get it. They're nice airplanes. My favorite plant in Brazil is a tree. It's the jabuticaba, and there's various reasons why it's my favorite. It's an absolutely strikingly beautiful tree. So it's aesthetically very pleasing, spreading like an elm, beautiful foliage, striking bark, beautiful white flowers that come right out of the trunk, and then a fruit that's looks a little bit like a big grape, but it tastes like a jabuticaba. It doesn't taste like anything else in the world. Very, very strong flavor. Great for eating directly or making all kinds of things from. So Brazil, like the US, has a lot of resource advantages. And they're largely unexploited right now. And I'm hoping that maybe a lot of them won't be exploited in terms of producing commercial products. On the other hand, in the south and southeast of Brazil, which was where I mainly work, there is a lot of development. If we look at Brazil's resources, a lot of them reside in the land. There's a potential area of 549 million hectares, 1.3 billion acres or something like that of potentially utilizable arable land. I sincerely hope that Brazil doesn't use that, even half of it. Right now, about 12% of that arable land has been exploited. The US about 40%, and of course countries like India and China, it's essentially 100% of their arable land is being exploited right now. A lot of this land is in some places that we consider the world. The world believes it belongs to us, and Brazilians kind of would like to keep it that way. But Brazil wants a developing economy too. In terms of energy, if you pull into a typical Brazil gasoline station, it's not a gasoline station. They sell gasoline, but nobody's going to buy it because the alcohol is a heck of a lot cheaper. And then the diesel is largely produced from biodiesel. This alcohol comes from sugarcane. This is during the low season, and sugarcane alcohol can be as little as a third the price per liter as gasoline. Of course, fuel in general is quite expensive in Brazil, like it is in most of the rest of the world too. This is my latest car. It's a Fiat. It's a 1,000 cc car. I wish I could buy something like it in the US. It's a flex car. There's a little thing, flex here. Flex in Brazil means it can run anything from 100% gasoline to 100% alcohol and any mixture in between the two. American cars can't do that. Airflex cars are 85% maximum alcohol. I love this car. Fuel also is produced, in this case, it's firewood is extensively used in Brazil in the mix. This is a very rural area, homemade kiln, and they're piling wood in here that they've cut out of natural forests nearby. This is deforestation is a serious problem in large parts of Brazil. And then in terms of air pollution, this is the destructive distillation of wood, basically wood heated to high temperature without the presence of oxygen to produce charcoal. And this charcoal is often used. Every Brazilian has a churrascaria where they grill food. And they often, many people do this every single day, but it's always done for parties. If you go to a Brazilian party, there will be churrasco. I mean, it's like the 11th Brazilian commandment or something. This carbon is also used to fuel the metals industry. You have to have a reductant to turn iron oxide into iron, and carbon is the industrial reductant. So that carbon will be ground, in some cases, and mixed and used to make steel and aluminum. Right now, the Brazilian energy mix is about 50-50, renewable resources, a little bit less than 50%. And about half, a little bit more than half of this is plant resources, is biomass. So the US has a goal, I think, to be 30% renewable resources in the next 25 or 30 years or something like that. Brazil's already there, and their goal is 70 or 80% in the next year. I don't even think that the US has a stated goal to be 50% renewable energy anytime in the future, at least by anybody serious. The world mix is something about 13% renewable resources in their energy mix. So Brazil in some ways is way ahead of the world. On the other hand, this results in the utilization of a lot of land to produce the biomass. We're talking about a complex system of biorefineries where eventually Brazil and the rest of the world hopes to be supplying chemicals and plastics and things like this rather than having them come out of petroleum. So wood would be in the Brave New World kind of sense, you make lots of different things from biomass. I'd mentioned Brazil has most of the tropical forests. There's two distinct tropical forest types. The Amazon, which is largely intact, very little disturbance. There's some schools of thought that think it's been a lot less disturbed in the last couple hundred years than it was for thousands of years before, but a bit in peril because of encroaching development, particularly along the margins. And then the Mata Atlantica, which is what I'm going to talk about. The Mata Atlantica, because of agricultural and development, is pretty much gone. This is the yellow area was the original extent, and the green area is where prime, relatively undisturbed Mata Atlantica exists. Something on the order of 10%. This doesn't show well, but this is south and southeastern Brazil, just an enormous network of roads. And this darker area, south of the biggest city, 20 million people, these are among the areas that have the most intact Mata Atlantica. It's interesting because it's closer to the city and the wealth and the industry. Inland, essentially, it's all gone because of agricultural development. Most of Mata Atlantica is associated with very difficult areas to get to. So mountains. Here, for instance, is a trip that I took into Mata Atlantica in São Paulo State, in fact. And this guy's taking his cable out to hitch it to a tree to pull himself out of this hole. The mud is all the way up to the well, and he's riding on top and dug into the mud there. In this case, getting into the Mata Atlantica took us 3 or 4 hours to go maybe 5 or 6 kilometers. But when you get in there, you find an incredibly diverse forest. Many people say the most biodiverse forest in the world, certainly more biodiverse species per hectare, if that's your calculation, than the Amazon, more biodiverse in some ways than the dipterocarp forests of Indonesia, Central Africa, and so on. But it's just a very impressive, biodiverse, very dense forest that's largely gone. Here's an aerial just south of São Paulo, which is about a 5 by 9 kilometer area, no roads, no nothing, no people, just intact Mata Atlantica. Very unusual. As I said, about 10%, and it's relatively unusual to find this size of an area in Brazil. Usually it looks more like this, a mixture of agricultural uses. In fact, this is an improvement district where they're starting to actually not march their cattle right down into the streams. So the stream, the bacias, are being protected in this improvement area, but largely there's no significant forest land and no Mata Atlantica. As I said, we got about 10% in Brazil left. It varies depending on the states, and the most developed states of Brazil include the highest proportion of intact Mata Atlantica, probably because they had wealth early, and then the wealth led people to be willing to protect areas. What does intensive forestry do? Well, if you think of economy and efficiency, you can have miles driven per gallon of gasoline used. You can also, in different vehicles, have different efficiencies. We can have the same thing in forestry. So we can have non-production forest lands that don't produce any wood, all the way up to increasing levels of technology that produce more and more wood per hectare or per area of land used. So I'm going to be talking about why we can use technology to actually protect Mata Atlantica. In 1989, for instance, about 1% of Brazilian forest land was in intensively managed plantations, and plantations in general. Produced 35% of Brazilian forest products, about 80% of pulp and paper, only about 8% of energy wood. 92% was cut from national forests. In 2011, the percentage only increased to 0.5%, but that industrial plantation type forest produced 60% of all Brazilian forest products, including about 10% of rural energy wood. So still 90% is being taken out of natural forests. In that period of time, the total production from Brazilian forests tripled from about 60 million cubic meters to about 180 million cubic meters. And in comparison, in 2001, Brazil produced about 100, the US produced about 400 million, for about 4 times the Brazilian production. Essentially, all of the increase in productivity was because of application of technology. So I would propose that we would take land like this. In fact, this is occurring right now, and I'm part of the research. Heavily degraded land, and this is 2 months after planting that area to a eucalyptus plantation. 6 years later, you have 350 cubic meters per hectare of biomass on that land, of wood on that land that's highly valuable. And in fact is eating a lot of the US's pulp and paper lunch in a lot of ways. But equally important is about 20% of the land area by law is set aside. Nothing has to be done, so it often regenerates naturally. And then that, in this case, 3 years after it's no longer grazed or farmed, is developing a diverse forest. You can see the difference between the road here. This is an improved agricultural area where the waterways are being protected, and you see just a few little areas of forest land. And then this is a forest plantation. This coarser textured material is regenerating natural forest in a matrix of mostly eucalyptus plantations. So research has a role in this as well. Key is the soil. These soils are highly degraded. We're not replacing forest with forest. We're replacing degraded ranch land, grazed in some cases for hundreds of years with forest, with intensively managed forest. Soil is highly degraded. What we're finding is there's not a whole lot of resilience in these intensively managed plantations. Inputs are critical. You can't just plant trees. It doesn't work that way. You don't produce much. If you abandon it, it regenerates to many, many species, most of which aren't commercially viable, at least yet. So nutrient cycling studies show that we need to be very careful about how we manage these lands. Research is key. This guy here, José Leonardo de Gonçalves, he's a professor at Unesp, University of São Paulo, and he has done more than just about anybody. He's been to the US several times, been to the UW, and in terms of managing soil, including removing material and redistributing bark on sites that are growing eucalyptus with the idea of maintaining the integrity of the soil in these systems. Also, waste material typically hasn't been utilized in Brazil. Brazil's cleaning up its water now and producing sewage sludge, which is also being utilized in these kinds of forest systems. It's also used in the cane sugar industry a lot, too. But in this case, you have a eucalyptus, a very highly eroded, degraded soil here, and then this organic matter and nutrients can effectively improve the quality of the soil. We don't know much about the natural forests. Right now, a lot of the work is just cataloging the species that are there, which are incredible. In some cases, hundreds of species on a single hectare of land in the natural forests. On the other hand, carbon sequestration ideally could be sold, so some of the work is being to develop biomass equations. And also the potential for utilization of nursery practices. This is a field trial of 12 native species, and this guy's doing a lot of work in trying to figure out how to regenerate these and then possibly plant them, particularly species that have high ecological value. The Renascer de Serra means the rebirth of the forest, and I hope you maybe understand a little bit about how we can utilize, remember in a degraded landscape, intensive forestry to both protect the native forests that are still there and also to increase the amount of Mata Atlantica over time by having areas that are dedicated to being returned to their natural state. Thank you.
Our next talk is by Ken Bible, who is currently a research scientist and manager of the Wind River Field Station in South Central Washington. And he earned his PhD in ecosystem sciences from the College of Forest Resources in 2001. And his research focuses on ecosystems responders to changing environmental variables. And he's collaborated with many researchers, is involved with a large-scale environmental data networks to answer global scale questions. And the title of his talk is The Wind River Field Station, a wildland forest ecosystem in a multinational carbon monitoring network. Ken?
Thanks, Bob. I express my appreciation to Bob for this invitation. I live in the boonies and I work in the woods, and coming to Seattle is a vacation for me. Little housekeeping to start off with. The station, the Wind River Field Station, operates from an agreement among the School of Forest Resources here, the research station of the Forest Service, the P&W branch. They are a major funder, and the Gifford-Pinchot National Forest, which is in the regular National Forest branch. The reason for the heavy-duty Forest Service presence is that if you drive south on I-5 down to Portland, catch the Columbia River, go up about 60 miles, you end up on the Wind River Experimental Forest, which is on the Gifford-Pinchot National Forest, and that's where the site is located. It was Jerry Franklin who championed the startup of this research station. He was looking for a place for an old-growth canopy observatory, a place to site the Wind River canopy crane. We focused in on the Thornton Taft Munger Research Natural Area, which is in the experimental forest, and research natural areas are set-asides of unique ecosystems, and this unique ecosystem is a 500-year-old Douglas fir hemlock old-growth forest. You can see from these images it's a very heterogeneous structure and composition of this canopy, and that's what he was particularly looking for. And if we look in the understory as well, we find a rather lush and long time since disturbance understory. These pictures are a little bit misleading because I was studying communities as you get close to logs, but it's okay because there are a lot of logs on the forest in here, which is exactly what you would expect in an old-growth forest. Since the beginning of the Wind River Field Station and this old growth patch, several other groups that are interested in having networks, and they want kind of like a scientific control, a piece, one of their sites has to be in unmanaged forest, and hopefully, preferably late successional forest. So one of the first ones to come along, of course, is the U.S. Forest Service Experimentation Station, which we're part of the PNW, which is in Portland. And they help us out. That first network has plant databases, animal databases, fungi databases, all the biodiversity sizes, numbers, and changes over time. Right on the heels of that is the Forest Service Climate Tower Network, and they bring us Class 1 sensors for measuring air temperature and precipitation, and also fast isotope lasers for carbon stable isotope lasers. The AmeriFlux program was started by a group out of UC Davis. I've since inherited that one. We'll talk a little bit more about it. The AmeriFlux is our regional network, and that really should read North and South America to the global CO2 flux community, which is FluxNet. I'm going to come back to that in just a minute. Next one's the Biogeosphere Atmosphere Stable Isotope Network, or BASIN. This is a group out of University of Utah and also out of San Diego. They monitor stable isotopes of carbon, oxygen, hydrogen. The Smithsonian Group has a network of large plots all over the world, and the installation at Wind River is actually, the PI for that is Jim Lutz, who's here at the School of Forest Resources as well. We have the PhenoCam program, which is out of Harvard, and this is a calibrated optical camera that keeps a watch on the forest every day, every half hour, letting us know when the spectrum changes of that canopy, so to try to understand when does spring occur, and that's going to be important. I'm going to come back to that. Cosmos is the new one on the block. It installs this summer. This is the brave new world of cosmic ray hydrometeorology, and this is cosmic rays bombarding the soils, giving off neutrons. We can measure soil moisture this way, so you got to be a bit of an engineer to get into this site. Now, all these people come together, and they bring something to the site, and they can work together. The plot people get the meteorological data, the isotope people get the carbon flux data, so they all kind of get something, so the whole greater than the sum of the part kind of thing. But if all of us push together at the site, we can answer global questions, and one of those is CO2, dynamics across the entire world. Well, let's just step back a minute. Why CO2? The first one is carbon, of course, all of its cycles, a solid, liquid, gas. When it's in its gas phase as CO2, it's the easiest for us to sample. It's also that pool of CO2 in the atmosphere that the plants are taking up in photosynthesis and fixing as carbon into carbohydrates and other biochemicals. Carbohydrates are then burnt by the plants for their own metabolic needs. We'll eat the plants, the fungi eat the plants. Eventually, some of that carbon dioxide that was taken up is respired back into the atmosphere as CO2. You can also burn, mass as an external energy source, which, Susan and Christina and Rob have talked about quite well. Once it's all taken in from the atmosphere, then burnt either internally or externally, it's going to get back into the atmosphere, and then we get to one of the more hot topics of today is the greenhouse effect. Carbon dioxide is a major greenhouse gas, not the only one, but a major one, and it's one that does help dictate about our environment here on Earth. So it's important. The short answer is we should be watching out for CO2 because, quite frankly, it's about life on Earth. Well, the question before us, I hear from kindergartners in my local school all the way up to policymakers, is how much carbon can the forest take in? Well, not really the problem, but the solution is we have to have a standardized sensor that everyone can use, and we have to have a standardized way of using that sensor and then a standardized way of analyzing those data. The first thing you have to have is a eddy flux system. You have to have some kind of way of managing, of taking in information about this exchange area between the atmosphere and the biosphere. And from now on, I'm only talking about forest and the biosphere because it's thought that much of the CO2 being taken in from the atmosphere will be taken in forest biomes. Eddy flux theory is that all the wind moving through the forest, either from the ground level all the way to just above the forest, is moving in these eddies that are connected. They have moisture connected, they have particulate matters connected, they have energy connected. Eventually, they make their way up into this exchange area, and that's what this pink arrow going across is supposed to signify. So using a tall tower, the idea is to stick this sensor in right into that exchange zone, and the sensor takes in a sample of gas and also has a high-speed wind and speed and direction indicator, so you know where that sample of gas was coming from. In a good day, that tells us the amount of carbon either coming up or back into the forest, in or out of the atmosphere. But The carbon that's coming off of the forest is a net between carbon taken in by photosynthesis and carbon given off by respiration of all the organisms on that forest floor. Fungi and bacteria included in this. So we call that net ecosystem exchange. It's also called net ecosystem productivity if you're a forester. You can see this tower here. This is the tower of the Wind River Canopy Crane right here. About 70 meters off the ground. This is the boom that sticks out over the forest. It has the gas intake and the sonic anemometer. Brings that into the infrared gas analyzer, and we can monitor the carbon dioxide exchange. We monitor it 10 times a second, and from those data, you can do all kinds of analysis. So we have a particular sensor that everyone's going to use. We have to have a standards and operations type of network where we all get together and agree on how we're going to use this sensor, how we're going to exchange the data with one another, and how we're going to analyze this data. That way, we can spread all over the entire globe and everyone have the same data, make it comparable. That's where FluxNet comes in. Ameriflux is our regional network, which takes up North America, South America. There's lots of 30 different regional networks. There are right now 500 participating sites in this network. So what have we learned? We've got the sensor, we've got the network. In 2007, we had a publication came out by a large group of eminent biologists that are in the flux community. And they used data from 2005, 2006 for the global forest, where there were FluxNet sites. I just want to kind of stress just how recent this kind of analysis is. 2007 was the first baseline analysis. This particular graph, this chart, I pulled out of that publication only for the net ecosystem exchange. They did all kinds of analyses. One of their goals was to create this really smooth data set that they could hand to other people. And later, as time goes on, refer back to it, see how things change. The first thing they did, of course, was try to cut up the world's forest into specific biomes, which is quite a challenge realistically. I mean, how many biomes can there be? If you cut them quite thinly, you can get a lot of them. Well, they used a system by Wright, published in 2002, where you take mean temperature, mean maximum temperature, mean minimum temperature, mean precipitation, and then one major growth form, which is either deciduous plants or evergreen plants. Really quite simple, but when you got quite a few sites, these broad categories allow you to include these folks. The two sets of numbers you see here are highs and lows. The lows are really 25%, the mean of the lowest 25%. The high numbers are the mean of the highest 25%, so you kind of have this smoothed high and low. And these numbers are grams per centimeter squared. And this is a very small unit. However, it's a unit that allows us to compare all different sites and look at the magnitudes. The numbers in the parentheses are the number of sites that were included. There are 130 sites in this study. So by 2006, there were only 130 sites, forested sites in FluxNet, that could be used, that had enough data to make it into this study. Again, that's just how recent something like this is in our world today. Well, when they got to analyzing the data, and they came to the net ecosystem exchange, you see that the top 4 highs are in the 500s grams per centimeter squared. Well, that's really quite high. And that was surprising that there was so much carbon being taken into the ecosystem. It's not till we get down into the dry and cold, the temperate semi-arid to boreal semi-arid, that there's a huge jump in the carbon uptake. As a matter of fact, we even see our first negative numbers. When the number is negative, there's actually carbon going from the forest into the atmosphere. If the number is positive, it's going from the atmosphere into the biosphere. So until we start seeing the dry and the cold, we get this big shift in the numbers. Well, in the conclusion of their paper, they said, well, temperature and moisture are probably not good indicators of net ecosystem exchange. In fact, they were right. And so we can examine this a bit by coming back to the Wind River site and looking at 8 years of data that started in 1999 through 2007. Temperature and moisture are good indicators, good variables for estimating photosynthesis, estimating the carbon in, but they're not good indicators for estimating the carbon out through respiration, because photosynthesis occurs that year, but respiration has all different kinds of lags going down from what the plant's going to use, what the fungi are going to use, what goes into the soil and eventually gets burnt. So lots of lags in that. This is a carbon update period. This is where I actually get to be a scientist rather than a manager or an engineer on this site. And I'm working with a former PhD student who's now at Lawrence Livermore. And these numbers are actually different sign because she's an atmospheric biologist and she tends to think of sources and sinks at the atmosphere, not in the biosphere. It's just one of the funny things these atmospheric people do. So the numbers are still the same, but they just have change in sign. So if we look at the range, which is in parentheses, it'll be, let's think of negative 78 to 233. That really fits into the boreal humid category, not the temperate humid category, which this site was classified. So here's another change where we got to figure out a way of classifying our sites other than with these basic biome of moisture and temperature. One of the things that we're going to install is the Cosmos probe this coming year, and the Cosmos probe, again, is this way of going from, we measure soil moisture by a few points in the soil and average it over the whole site. Well, the Cosmos probe can measure average soil moisture over a 700-meter diameter circle and down to a meter underground. So it's thought that if we can get temperature, precipitation, and soil moisture, maybe then we can start modeling respiration better. And that's probably true, hence why the Cosmos probe is going in. Now, if we look at these graphs, this is an analysis technique of just starting the year at 0, and then every day averaging whether you're a source or a sink, get an accumulative change throughout the day. If we look at the top line, which is white, that line came out in 2003. That was a very dry and warm year. The bottom line is black, and that came out in 1999. That was a cool and wet year. So we were thinking, and so this is about 1999 to 2003, and we're thinking, oh, great, we've figured it out. We've got the warm and the dry. Well, we fell into that trap because years later, and even up to 2009 and 2010, which we're working on right now, the data, the pattern is pretty much the same. It just shifts a little bit. So it's not, the respiration is not dependent on temperature and moisture. What we did get, though, is what we set out for in the first place. We have a quantitative, objective way of monitoring an old-growth forest ecosystem's carbon footprint. Not carbon footprint, sorry, the carbon pattern through time. This pattern keeps repeating itself, keeps repeating itself. What we have to be looking for now is the change in that pattern. Now we have a standard pattern. One of the changes you see is about day 150. You have a nice coherent pattern that's all very tight going down to about day 150. And then everything starts to shift. Well, day 150 is the end of May. So what's happening out there right now is the plants are putting out pollen cones, are putting out seed cones, they're busting their vegetative buds and putting out new branches and new foliage. So this is what's shifting that graph right now. Hence why we have the phenocam program there. We need to keep a track on when is that occurring, match it up with our eddy flux system. Good way of monitoring this ecosystem. That's another, one of the reasons too you need long-term data to keep from fooling yourself on short-term data. So the research now is going to different sites and finding out what that carbon uptake period pattern looks like. What does a disturbed site look like, a younger site look like? So now, because we have now the primary pattern in an old-growth forest. Two thoughts I'd like to leave you with. One is if society demands, we have certainty in understanding carbon dioxide exchange in the atmosphere and the biosphere, there has to be investment in these capabilities. Modernization and of these sites, and also just some examples of this, the National Science Foundation funds a long-term ecological research program, which does just this very kind of thing. They just spun off a nonprofit called the National Ecological Observatory Network. This is an interesting addition. The Wind River site is actually chosen to be in this network, which starts in 2013. Rather than sites like we have now that all came up from the bottom for different research purposes and then agreed to be in this network and share data, the NEON network is actually built from the top down and fully funded, and it's going to be imposed to do exactly this. So we have a completely different way of going about this. The last one is that if you're going to have these networks, you need not only people to analyze the data, but you need people that actually run these sites and understand these data. The Wind River Field Station and many of the field stations that are in FluxNet are good practical training grounds. And I'm not talking about taking semesters there, just 1 week. Just a couple of weeks ago, I had some folks from San Diego who are laser isotope folks, and they have an intake at 1 meter, and they wanted to know about the plants that were there, and they were hot on my heels all week showing me pictures of all the plants they'd taken because they didn't know anything about those plants. But just a short time, they began to appreciate the biodiversity. I see that in the professionals as well, because they know that the ecosystems are complex. It's good to have a discipline, but you also have to be able to emphasize other disciplines to do it well. Ecosystems are complex. That's okay. It doesn't have to be simple. After all, we're talking about life on Earth. Thank you.
So, our last talk in this session is by Barbara Clucas, who is a postdoctoral researcher and has been working with Professor John Marsliff in the School of Forest Resources for the last 2.5 years, and first in Berlin at Humboldt University in the Urban Ecology Group, and now at the University of Washington. And she received her PhD at the University of California, Davis, in animal behavior. And her research areas are animal behavior and urban ecology, and the title of her talk is A Cross-Continental Comparison of Ecological Connections Between Humans and Birds in Urban Areas. Barbara.
So I'm going to switch gears a bit here and talk about wildlife and humans in urban settings. Humans and animals have been interacting for thousands of years. We were first prey items ourselves, and then we moved to being skilled predators. In the more recent past, we became domesticator of wild animals. Currently, we still interact with wild animals in natural areas through sports and hunting, as well as conflicts that arise when human developments encroach in wild areas. However, we also interact with animals in urban areas, such as companion animals, dogs, cats, or species that humans consider pests, such as rats or cockroaches. We also have a high probability to interact with birds in urban areas. So certain species of birds occur at high densities in urban areas, and we were interested in looking at the consequences of these interactions between humans and birds in urban areas. So birds living in urban areas face several challenges. So they're dealing with new habitats, human traffic, but there are also many benefits for them living in urban areas, such as novel food sources, whether intentional or unintentionally provided by humans, as well as the fact that there are fewer natural predators in urban areas than in outlying areas. Humans living with birds in urban areas have some negative aspects, so birds can disrupt waste, and they also have been shown in the recent past to transmit disease, such as the avian flu. But they also provide positive aspects. So it's well known that a view of nature provides or promotes health and well-being in humans, as well as providing an aesthetic quality to urban areas. So what I hope to show you today is that we've found that human actions can also influence bird diversity and behavior in urban areas, and that recent research suggests that higher bird diversity can benefit human well-being. So this creates a potential positive feedback loop between humans and birds. So our research methods involve two phases. First, we surveyed human attitudes and actions, and then we surveyed bird diversity and behavior across our sites. We did this research in 2 different cities, Berlin, Germany, and Seattle, Washington, to get differences in cultures, human culture, as well as across an urbanization gradient, moving from the city center out to more rural areas to get different habitats and different demographics. Our 2 study sites, as our photos show, are very similar. We have both cities are large green cities, and they also have similar population sizes of about 3.5 million people. But there's also many differences, the first being that Berlin is a much older city than Seattle, as well as cultural differences that exist between Germans and Americans. Now, our study sites go across an urbanization gradient, starting in urban areas, moving through dense suburban, light suburban, and rural areas. And they're defined by the density of humans, thus being higher in the urban areas and decreasing out to rural areas, and as well as the percent of vegetation found being least in urban areas and increasing as you move out to urban areas. And in our first phase of our project, we conducted surveys on humans, going door to door, conducting personal interviews, about 30 per site. And we asked residents about their general actions towards birds, as well as their specific attitudes between finches and crows. So the actions that we asked humans about at different sites directed towards birds were either if they were provisioned birds or discouraged birds. So provisioning birds, we asked them if they provided food or nest boxes, which cavity nesting birds use, as well as discouraging behavior, such as putting up predator decoys or shooting or chasing birds. And we found that the results varied between our 2 cities, as well as across the urbanization gradient. So in our first graph here, we show the percentage of residents that are feeding birds in the two cities. So for the rest of my talk, my graphs will have blue for Seattle and yellow for Berlin. And we also show the differences across the urbanization gradient. And we first found that there was much more feeding of birds in Berlin than in Seattle, and that they differed in their the patterns across the urbanization gradient. So in Seattle, we found that there were highest levels of feeding in the rural areas and then decreasing linearly into the urban areas. Whereas in Berlin, we found there were very high levels of feeding of birds in the rural and suburban areas and decreasing in the urban areas. We found a similar pattern in the percentages of residents providing nest boxes. So again, we found more provisioning of nest boxes in Berlin than Seattle, and we found that there were differences across the urbanization gradient in both cities, with having the least amount in the urban areas and more in the suburban and the rural areas. Now, for the discouragement of birds, we found a slightly different trend. So here we showed that there are differences between the cities because there was more discouraging behavior of birds in Seattle than Berlin. And this relationship was caused by the fact that there was the most discouraging behavior in the rural areas in Seattle compared to the other, the suburban and the urban areas. And there was also differences in the types of discouragement behavior. So Seattleites tended to be a little more aggressive in their discouraging behavior, putting up spikes, nets, throwing, shooting birds with the intent to kill, putting out bottle rockets to scare the birds with the noise, as well as putting up predator decoys. Whereas in Berlin, there was some more passive behavior, so putting up nets, yelling, hand clapping, or setting up predator decoys. So in the next part of our survey, we wanted to ask humans about their attitudes and actions between two different bird species. And we chose finches, the green finch in Berlin and the house finch in Seattle, as a charismatic species that we expected people to have positive attitudes towards. And then crows, the hooded crow in Berlin and the American crow in Seattle, as species that people might have more negative attitudes towards or consider them nuisances. And we asked them specifically about how they felt about the visual aesthetics of these species, as well as if they directed any discouraging behavior at these species. And overwhelmingly, we found in both cities that people much more prefer the appearance of finches over crows. So both the green finch and the house finch in Berlin and Seattle were preferred over the crow species. And this preference translated to their discouraging behavior. So we found no discouraging behavior in either city directed towards the finch species compared to that of the crow species. And we found more discouraging behavior directed towards American crows than hooded crows in Seattle and Berlin. So overall in our human survey, we found there were differences at different levels in the human attitudes and actions towards birds. So we found differences between the cities, across the urbanization gradient, and also towards different species. So specifically, we found that there was more provisioning behavior in Berlin than Seattle, and there was more discouraging behavior in Seattle than Berlin, and that there was more provisioning in the rural and suburban areas, and more discouraging behavior in rural areas in Seattle. And we also found that people tend to find crows less visually pleasing than finches, and they discourage crows more than finches. And so for the next part of the project, we wanted to see if any of these differences in human behavior affect bird diversity or behavior across our sites in our two cities. So for that first part of the second phase, we looked at bird diversity, which is just simply the number of different bird species. And we were particularly interested in the number of species that are using feeders and nest boxes, and looking to see if these number of bird species relate to the human provisioning we found. And this is indeed what we found. So in this graph, we show that the percentage of residents that are feeding birds directly affects the number of species using feeders. So there's a positive relationship between these two factors in both cities. So sites where people are putting out more feeders, there's a higher number of species that are using these feeders. And we find a similar pattern with the number of species using nest boxes and the percentage of residents that are providing these nest boxes. So again, in both cities, there's a positive relationship between these two variables, and the higher amounts of nest boxes that are provided by humans creates more species that use these nest boxes. Now, when thinking about this human-bird relationship, there might be two possible reasons why this relationship exists. So it first might be that humans providing these additional resources might actually increase the species of seed eaters and cavity nesters. But it's also possible that there was a greater diversity of these species to begin with, and that actually promoted humans to put out more feeders and nest boxes in these areas. And it's also a possibility that there's a combination of both of these factors. So in the second part of our phase 2, we looked at bird behavior, and we wanted to look to see how birds reacted to humans. And we did this by testing their flight initiation distance, which is just simply the distance at which a bird flees from a human when walked or approached by a human. And we tested our 2 crow species, again, hooded crows in Berlin, the American crow in Seattle, and we tested 2 similar to finches in their charismatic qualities, the house sparrow and the American robin in Berlin and Seattle. And this was due to the fact that all these species occurred across our sites. And we found several factors that influenced flight initiation distance. First, the urbanization gradient had an effect. Second, the types of species changed their flight initiation distance, as well as human discouraging behavior, particularly in Seattle. And this graph shows these differences. So here we have, again, our urbanization gradient moving from rural, suburban to urban. And on the y-axis, we have the mean flight initiation distance in meters. And as you can see, each species has a pattern of having shorter flight distances in urban areas, increasing into the rural areas. However, I want to point out this difference here in the American crow. So again, this is the area where humans are discouraging crows the most. And so we see that this translates into the increased wariness in the American crow in these rural areas. And we don't find that relationship with the other species. And so we found that human behavior influences bird behavior in both positive and negative ways. So human provisioning correlated with the number of species using these resources, increasing the bird diversity in these areas, and also that humans can negatively affect birds, such as we saw with the human discouragement behavior affecting American crow behavior in the rural areas in Seattle. So some of the differences that we saw in the human provisioning and discouraging behavior might be explained by cultural differences between people in Seattle and Berlin. So in a separate study, researchers have shown that attitudes towards wildlife different between Germans and Americans. So Germans were found to be more moralistic and naturalistic in their views towards wildlife than Americans. And Americans tended to be more utilitarian or negativistic in their views towards wildlife. And they also participated in hunting more than Germans did. And so these cultural differences may account for the differences that we saw in the provisioning behavior as well as discouraging behavior at our sites. So in conclusion, we showed that birds respond both to positive and negative actions of humans. And so the next thing to do is to look at how humans might respond to birds. And in fact, recent research has shown that countries that have higher species diversity of birds have higher life satisfaction, and that the psychological benefits of green spaces increase when there's a higher level of bird diversity at these sites. And so I think that when looking at urban ecosystems, we need to understand the links between humans and wildlife, and that this understanding can help understand the mutual benefits that can lead to a more effective wildlife conservation in urban areas. And with that, I would like to acknowledge the fact that this is an international collaboration between Humboldt University in Berlin and University of Washington in Seattle, my funding agencies, and the many research assistants that helped me. Thank you.